Welcome to this video on unconstrained optimization. First, we'll look at what global and local extrema are. First order necessary conditions to find these extrema, and then second order conditions to identify if they are maxima or minima. And then I'll go through an example and we'll solve this question together. All right, let's get into the video. So what is a local and global extrema? And I want to be really precise in my explanation of this. X star is a global maximum of f if f of x star is greater or equal to f of x for all x in the domain. And this is for a function f that maps things from some domain to the real numbers. That domain could be in higher dimensions, r squared, r cubed, but the output is in one dimension r. And yeah, it's a global maximum if all of the objective functions evaluated at a point in the domain are not as big as f of x star. It's a strict global max if this is a strict inequality. F of x star is strictly bigger than everything else. And it's a local maximum if f of x star is greater or equal to f of x for all x in an open ball centered at x with radius r that is intersecting with the domain D. Essentially what this means here, intersect domain just means that the open ball is inside the domain. And then part of this open ball is saying that if you look at x star and then you just go around it, if it's in one dimension, that's just looking left or right. If you go to the left or to the right of x star, you're going to decrease your objective function value for the points that are inside of this open ball. And usually the open ball centered at x star has some small radius. The radius can be as big as necessary, so long as for the radius, everything inside of that open ball plugged into the function has a smaller value. So an example of that is that this function here generates a local maximum at this point, and it's not the global maximum because when you keep on going further, eventually you'll rise up above it. But it is a local maximum because there exists an open ball to the left and to the right of x star where all of the function evaluated at points inside this domain will generate smaller values than at this x star. Notice that eventually it's going to start increasing above it, but everything inside of it is smaller than f of x star, and that's what makes it a local maximum. Now the same is true for minimum, it's just inverting those inequalities, so that is straightforward, and it's an extremum of f if it's a max or a minimum. All right, easy. And in optimization, our goal is to try and find these points, these maxima and minima, so that we can optimize something depending on the context. Okay, so first order conditions. To find these points, we can look at the critical points that satisfy the first order conditions, and this is what they are. If our domain is open and f is differentiable, then x in the domain is a critical point of f if the gradient vector is equal to the zero vector, i.e. every partial derivative is set to 0. And the theorem that follows this is that if x star is a local extremum of f, where the domain is open, then x star is a critical point of f. So what we have is that extrema implies critical point, which means that if it's not a critical point, it's not an extrema. And we can find all critical points of the function and then sort through them to see which one of those critical points are maxima or minima. Of course, they could be a saddle as well, which would be neither. That's why it's not necessary and sufficient. It's just a necessary condition that we can check through. Once we've found our critical points, we then use our second order sufficient conditions, which essentially is evaluating the Hessian matrix as to whether it's negative definite, positive definite, or indefinite. There's another video on how to do that more rigorously and comprehensively. But once you classify the definiteness of the second order derivatives, i.e. the Hessian matrix, then you'll know if it's a max, a min, or a saddle point. Okay, and yeah, I just want to reiterate that these are sufficient conditions. You can have maxima or minima that occur without this happening as well. And just because it is not positive definite doesn't mean that it's not a strict local minima of f. That's not enough for us to conclude that it's not a strict local minimum of f. And an example of that would be f of x equal x to the 4. So if you take the second order derivative test and you put it into the Hessian matrix, it's really simple because it's only one dimension of input. You will get a Hessian matrix evaluated at 0 of 0, which is not positive definite, but very obviously 0 is still a strict local minimum of f. So just be careful. These are sufficient conditions, but they're not necessary. You can get local minima without this happening. Okay, that's the theory overview. Let's now put into practice what we're doing by solving this question here together. Okay, so we want to find and classify all of the critical points. So let me just get these up and running. 1 second. There we go. Okay. All right, so this is the question. Let f be a function that goes from r squared to r, and it maps things from xy to x plus 3 minus y squared e to the minus x. That's our function, and we want to find and classify all of the critical points. So let's start off with our first order conditions. Okay, so our first order conditions is that the derivative with respect to x is equal to 0, and the derivative with respect to y is equal to 0. And in order for us to solve this, we need to, of course, differentiate the function. So let's differentiate it with respect to x first. Notice that this is the product of two things, and the left thing is in terms of x, and so is the right thing. So it makes sense for us to use the chain rule. U dash v plus v dash u. And if we call this u and this v, we can differentiate this with respect to x and plug it into this in terms of the product rule. So u dash v, u dash is just 1, and v is e to the minus x. So that's 1 multiplied by e to the minus x plus v dash u. So v dash will be minus e to the minus x. And then u is just going to copy in that from above. Okay, and if we combine these together now, this is e to the minus x, and there's minus 3 of them. And if we're adding in 1 e to the minus x, this is going to come down to just plus 2 of them. So ultimately that is simplified to this. All right, easy. And then fy is equal to the derivative of this with respect to y. And if we were to expand this out and then differentiate with respect to y, we'll get minus 2y e to the minus x. Okay, now that we have our two derivatives, we can set them equal to 0. So our first order conditions imply that e to the minus x, x plus 2 minus y squared is equal to 0, and minus 2y e to the minus x is equal to 0. And if these two equations hold, then we will have a critical point, because according to our first order condition theorem, this is the definition of a critical point, and that will generate our candidate solutions for extremum. Okay, let's look at this one. Well, e to the minus x can never be 0 as a function. That's just the way the exponential function works. And so clearly x plus 2 minus y squared must be equal to 0. So x plus 2 minus y squared is equal to 0. And for similar reasons, this is never 0, which means that y must be 0. So therefore y is equal to 0. Okay, and if we know y is 0, then we can plug that into this one. And we have x plus 2 is equal to 0, so x is equal to minus 2. And that is the only way that these can both be equal to 0 at the same time. So therefore, minus 2, 0 is the only critical point. Okay, now we want to classify it. So to classify it, we want to evaluate our Hessian matrix. So let's look at that. I just try to make this working extra clear. So we've done our first order conditions to find our critical point, and our second order conditions will give us insight as to the nature of this critical point. So according to our second order sufficient conditions, we want to see if the Hessian matrix is negative definite, positive definite, or indefinite. So let's work out our Hessian matrix. The Hessian matrix is defined as this. So let's work out all of these things. Okay, so differentiating fx with respect to x is differentiating this with respect to x. And notice that this is exactly the same as above, except with the 3 gone down to 2. And when we differentiate it, we're going to get the same outcome, but the 2 is going to decrease down to 1 according to this process outlined above. So we will have e to the minus x plus 1 minus y squared. Easy. fxy. What is that equal to? Well, we're differentiating this with respect to y. So combining expanding this out and analyzing the only y term is minus y squared e to the minus x. So differentiating with respect to y will give us minus 2y e to the minus x. Great. For context, like these, fxy is always equal to fyx. So that's the same. You can double check that if you are suspicious. And then last one we have to work out is fyy. So differentiating this with respect to y is going to be minus 2 e to the minus x. Okay, and now that we have all of those, our Hessian matrix, we can factor out e to the minus x and then plug in everything. Got x plus 1 minus y squared minus 2y minus 2y minus 2, which gives us this. And then evaluating this at the critical point, which was minus 2, 0, gives us e to the 2, plugging everything in, minus 2 plus 1, and then 0 is minus 1, that's 0, that's minus 2. And that's our Hessian matrix evaluated at the critical point. The last thing we need to do is determine its definiteness. So to do that, we want to have an analysis of the leading principal minus. So d1 is equal to minus e to the 2, and d2 is equal to e to the 2 multiplied by 2 minus 0. So that is equal to 2 e to the 2. What I'm doing, if you're not keeping up with that, I'm putting the E2 back in, and then the first leading principal minor is the determinant of this, and then the second leading principal minor is the determinant of the whole thing, which is what this is. So that the diagonals multiplied by each other, and you take the difference. Okay, and this is going to be less than 0, and this is greater than 0, and that is what we need to have a negative definite matrix. So therefore HF minus 2, 0 is negative definite. Therefore minus 2, 0 is a local max. And we're done. Okay, so that is the answer to this question. We've found all the critical points, which was just 1, minus 2, 0, and we've classified it by analyzing the definiteness of the Hessian matrix. It is negative definite, and so thus that point is a local max. Alright, thanks for watching this video on unconstrained optimization. I hope you found it helpful. Alright, see you next time.